Hi, I'm Laura Stegner, a PhD student at the University of Wisconsin-Madison, and today I will present work on behalf of my co-authors called Situated Participatory Design, a method for in situ design of robotic interaction with older adults. We present a novel method for designing technology with older adults that uses situated, realistic, repeat interactions with the target technology. This helps us engage older adults and better understand the real-world challenges of technology use and integration. Our work is motivated by an increasingly aging population. People are living longer and they want to be more independent and live healthier lives. At the same time, there's a growing shortage of caregivers, so people have been turning to technology, such as robots or other AI systems, to help. As we develop this technology, researchers have found enormous value in including older adults directly in the design process through co-design and participatory design methods. This involvement leads to a better understanding of older adults' needs and challenges, which results in better designs and ultimately better acceptance and adoption from this population. So we want to design robotic interaction with older adults, taking advantage of these benefits. Specifically, a robotic interaction to help with some daily care tasks for older adults, such as picking up something from the floor or making a small delivery. We want to consider questions such as, how would people interact with this technology in their daily life? Would people accept this technology? And what practical insights do we need to consider? While co-design shows great promise, there are some known challenges of working with older adults that make this kind of holistic design question difficult to explore using current methods. Older adults can have cognitive challenges with grasping intangible or unfamiliar concepts, such as robots or new technology, and they can also struggle to use their imagination. They could also have physical challenges related to completing study activities such as sketching or drawing, or even traveling to the study location itself. There's also ecosystem-level challenges related to considering not only the older adult and the technology, but also how it fits into the greater environment. And finally, we have to consider the other stakeholders, such as family or caregivers. What are their views and wishes? To address these challenges to better design with older adults, we introduce our method, Situated Participatory Design. This paper focuses primarily on the method we used, so we won't go heavily into the details of our design results, but instead overview the method, then walk through an example from our case study, and finally discuss the benefits we found from our method and how it can apply to other contexts. This is Situated Participatory Design, a three-phase method intended to better engage older adults in the design of assistive technologies. In Phase 1, we introduce the robot and select and design an initial task for the robot to do. In this phase, the researchers are in the room with the participant and the robot, working together to help generate the design. After that, the researchers remotely control the robot to walk through the interaction in a user enactment to give the participant the chance to experience it and provide early feedback or make changes. I'll now show a brief video clip of one resident walking through a handoff while we remote control the robot and discuss how the robot should interact. Do you want it to hand it to you,
Yes.
or put it down somewhere?
Hand it to me.
Hand it to you?
I will open the hand now.
Is it? Other way, other way. Yeah. And do you want it to say anything while it's doing that?
No, not necessarily.
Next, Phase 2 introduces several short, realistic encounters with the robot, which we call simulated deployments. In Phase 2, the researchers are still remote controlling the technology, but they do so from outside the participant's room in a Wizard of Oz-like method, creating a more genuine interaction context. The robot also initiates the interaction as it might in a real deployment. The time is roughly set in advance, and the robot arrives without extra warning to the participant. After the simulated deployment, the researchers enter for a quick debrief to see how it went and note any changes they wanted to make for the future. Multiple simulated deployments take place over the course of several days to allow more time to iterate and improve the design. Here you can see the interface we used during the study to remotely operate the robot, including the camera feeds that we streamed from the robot to drive it around, and the speech interface we used to type what the robot should say. This video shows a brief clip where the robot is delivering a cup of ice to a participant to use with their afternoon beverage. Then, in phase 3, we seek feedback from other stakeholders. In our case, we talked to caregivers at the facility to get their input on the tasks the residents designed for the robot and other higher-level considerations the residents may not have thought about. The following video shows the caregiver discussing seeing the robot around the facility and hearing about the residents' scenarios.
It's invigorating. I mean, it's wonderful for multitude of reasons. I think it can complement the caregivers so well in some of the things day in and day out. We, the caregivers, can focus more on quality than doing all the legwork.
We implemented Situated Participatory Design at a local senior living community where we worked with 9 residents and 3 caregivers to complete in-the-wild human-robot interactions. There are many results and insights in our paper, but now we will walk through one example of how the design process went for one of our residents who designed a mail delivery scenario. In the initial design in phase 1, the resident wanted a fairly basic interaction. They wanted to receive an automated phone call with the option to accept the mail delivery or not. Then the robot should arrive, simply knocking and directly entering. The robot knows in advance where to put the mail, and then leaves and says goodbye. After the user enactment at the end of phase 1, the resident requested a few changes. This time the resident wanted the robot to also speak to announce its arrival. And then they directed the robot specifically where to put the mail instead of using the pre-specified location. Interestingly, when we tried to ask the resident after about how they wanted to interact with the robot, they could not articulate what they wanted, and instead we could only uncover that detail by trying the interaction and observing the resident's behavior. So now we come to the simulated deployments. After the first one, the resident wanted more changes, which we believe is because the researchers were not there to mediate the interaction with the robot, and instead the resident had to directly interact with it on their own. They found that they could not see the robot well as it slowly moved through the room, and therefore they wanted verbal updates on its progress. And the resident also wanted to engage in light chit-chat with the robot. After the second simulated deployment, the interaction becomes even more complicated. We found the resident wanted to have more complex conversation with the robot while it was in the room. And they even asked the robot to do another task while it was still there prior to leaving. So we can see that over time, the scenario really evolved based on the resident's experience with the robot. Overall, we reaped many benefits using our method. We as researchers got to see how well the technology fits into the environment, and the residents also got the same experience. We could learn together what worked for them, what the challenges are, and so on. We also got to vet the designs under realistic conditions through the simulated deployments. For example, once the robot showed up and the resident had a guest, so it turned into an unexpected multi-party interaction. And we got to see the practical challenges and considerations, such as we found the built-in speaker of the robot was not loud enough for some residents, and we also got to see how well the robot could interact with the residents' personal belongings. We believe situated participatory design could also be applied to other marginalized or vulnerable populations. This method worked well because the robot depends so heavily on the specific ecosystem and context of use, and it is difficult to capture that context in an isolated design session. We suggest this method could be used for many other scenarios, such as something like a cooking assistant for individuals with cognitive impairment, or developing a smart cane or other mobility aid for blind users, or combining with other methods such as those used by Chiltai and colleagues to develop a children's tutor in a community center. Overall, I want to leave with 2 key takeaways. First, we found that realistic interactions with the technology led to actionable input from older adults. This was really important, especially to help us overcome the challenges of imagining unfamiliar ideas. Second, bringing the scenarios out of the design sessions elicited unique insights into integrating the robot into the daily lives of older adults. Simulated deployments helped residents understand what it would be like to interact with the robot, and they were able to refine their ideas based on that experience. We as researchers also got to see the practical challenges of what happens when the robot is in the real world. We hope this method can help researchers create more robust designs and ultimately lead to more successful future deployments of such systems. Thank you for watching.